So I'm going to share with you tonight about the New Horizons mission, which is a mission that has launched to Pluto. And I'll give you I'm going to start out and sort of give you a history about Pluto to try to motivate why we think Pluto is particularly interesting as an object to go visit. And then I'll talk about the mission itself. I do have to say that some of the slides in my presentation I've taken from a variety of presentations that have been published by the New Horizons team themselves. So I'm not officially on the New Horizons team. I'm working with the New Horizons team members. And they've been very gracious to those of us who are sort of graduate student postdoc type position people who the New Horizons mission was first sort of thought about in the early 1980s, late 1980s. So most of the people that it's a fairly small mission compared to like the Cassini mission or the Galileo mission or whatever. And so most of the people who've been working on this mission, it's a small group of people, and they've been trying to do this for a long time. So anyhow, I'm indebted to them for their efforts in putting this together. I like this particular slide. So this was put together. This slide is put together as just an artist's conception. So this would be Pluto and the atmosphere of Pluto and Charon, its moon. And this was the stamp. So at one point, there were stamps that were developed for each one of the planets that were to be visited by spacecraft. And Pluto, of course, had not been visited by spacecraft. And at the time that it was discussed as being a mission, it was still a planet. And so this was the picture that was conceived of, and hopefully in a couple years we'll be able to really change what this looks like. So I'm going to sort of cover a lot of ground tonight, although sort of at a low level, or an overview level. So I'm going to talk about Pluto in terms of its discovery, Charon, which is its largest moon, a number of other moons that have since been discovered, and actually all of these moons, except for Charon, have been discovered since New Horizons launched, since the mission launched. I'm going to talk about our current understanding of the Pluto system and what we hope to learn when we get there with the spacecraft, the discovery of the Kuiper Belt, which provides some context for Pluto, and what we can learn by all the small bodies in our solar system. And then I'll just end by giving you sort of an overview of the New Horizons mission, what we hope to accomplish at Pluto, and then what we hope to do beyond Pluto through hopefully an extended mission. So Pluto was discovered in 1930 by Clyde Tombaugh, and Clyde Tombaugh was a Kansas farm boy. He went out to Lowell Observatory, and the telescope that you see here is the telescope he was working on. And what he would do, so today you take CCD images with your cameras, and he would use photographic plates. So basically imagine like a big, what would you have in 35 millimeter camera, except much larger, these glass plates that you'd stick in and observe for a period of time, take it out. He'd spend all night collecting data, and then he would spend the next day sleeping / processing and looking for moving objects. So he went out to Lowell Observatory and worked for a number of years doing this. And in 1930, they found an object, and I think the next slide has a picture, and found this object that looked like it was moving at the rate where it was projected to be in the outer solar system. Now, one interesting thing about the planets is that the terrestrial planets, Jupiter, Saturn, and Uranus, are all visible from the naked eye. Now, Uranus was not really known about until people discovered it with a telescope, but it's bright enough to be observed with the naked eye. Neptune was actually predicted based on two different mathematical groups that were working to predict that they should find a planet at the location, and they went with a telescope and looked, and lo and behold, there was this planet. And they predicted where it would be based on some oddities in Uranus's orbit. And so likewise, when they found Neptune, and they were doing studies of Neptune's orbit, they found some oddities in Neptune's orbit dynamics, and they predicted that they should find another planet at sort of the region where Clyde Tombaugh was taking data. And so when Pluto was first discovered, it was thought to be about the size of Mars. In the 1930s, so when it was discovered, it was called a planet because it was thought to be much more massive than it is now currently known to be, which is smaller than our moon. This is a picture, a discovery image picture. So if you look at these two stars here, and then you look at this little point of light at the end of the tip. And so what he would do is he'd blink these two objects, or these two images, back and forth, And after you look at enough of these, trust me, you train your eyes to find things that are moving. I've done a lot of this. This is a lot of what I spent my graduate work doing. Slightly different way of doing it. We used a computerized technology instead of a blink diagram. But anyhow, so he discovered Pluto, and it was moving at a rate, so you can calculate based on where it is relative to the stars, how fast it was moving, and it put it around 300 astronomical units. So distance from the Earth to the Sun, 300 times that. And it turns out it has a almost 350-year orbit. And when it was observed long enough to look at its orbital dynamics, we found that it has a very sort of odd orbit. So this is the inner solar system blown up here. So this is actually all fits down in here. This is just a zoom up. And then you have Jupiter, Saturn, Uranus, Neptune, and Pluto, where this orbit is actually inclined by 17 degrees. So it's not really in the plane of the solar system the way that it was expected to be. And it turns out that even though Neptune had some oddities in its orbit, it wasn't massive enough, didn't really fix the problems in Neptune's orbit. And some of the studies of the Kuiper Belt have since tried to understand what the dynamical situation is in the outer solar system. But when Pluto was discovered, it was sort of an oddity, but there was no way of getting any other information. It was sort of the faintest object that technology at the time would allow you to observe, and so they made the measurements that they could. Well, come along 1978, and James Christie was observing some data, or was using some data, reducing some data from the U.S. Naval Observatory in Flagstaff, Arizona. And in this particular image, he had a number of images like this where it looked like Pluto had this little bump on the top of it. And so after looking at enough of these images with blumps on them, and he noticed that this blob moved around depending on when he was looking at it. And so he concluded that Pluto had a moon. And so very close. And it turns out that Charon is pretty close to Pluto, especially in the way this image allows you to look at it. It's fainter than Pluto, 1/5 as bright. And with Hubble Space Telescope, we can actually resolve this distance between the two objects quite well. So this is using a telescope from the ground, like Magellan, which is a 6.5 meter telescope in Chile, or perhaps the Keck telescopes in Hawaii. And then this is using the Hubble Space Telescope, where you can really resolve the two components. If you take measurements over the entire orbit, so Pluto rotates in 6.5 days, and if you take measurements over the full orbit, you can actually track, this is the best map we have of Pluto and Charon at the moment, where you can actually track ices on the surfaces of this object. But this is like our highest resolution image that we have of anything at this distance from the sun. Once the New Horizons mission launched in 2006, which I'll get to in a little bit, it became a concern that there might be other material around Pluto. Pluto and Charon is thought in theoretically modeling its formation was thought to be formed through a collision. A couple tens of years ago, people started to think about collisions in the solar system and how that had influenced. We see planets; they have lots of craters on the surface. Clearly, collisions have happened. Have any of these? There was the idea that the moon formed through a giant impact with a Mars-sized object with the Earth. And so the question was, well, if that happened in the inner solar system, maybe it happened in the outer solar system as well. And it turns out that when you do a number of different dynamical models, that it's easy to form, maybe not easy, but not very difficult to form the Pluto system through a collision. So Pluto and Charon formed through a collision. And so there were some really deep HST surveys done using something like, I think, 20 to 30 HST orbits. And an HST orbit is 96 minutes, of which about 54 minutes you can actually use. And so they collected a whole bunch of images and stacked all the data. And so we have Pluto and Charon here in a short exposure. And then we find that there are these other satellites that show up when you do a bunch of careful processing of the data to show that these are real. And it turns out that there was actually data in the archive that could have demonstrated this, so we would have known about this earlier. But once you know something's there, it's easier to go back into the data that exists and find it. But it's not always easy to find it the first time around if you don't know what you're looking for. And so after you went through the database, you could find that you could get orbits for these objects. So these two have been named Nix and Hydra. Nix and Hydra. Pluto, kind of a cute story. So Pluto, Percival Lowell was the founder of Lowell Observatory, and Pluto was discovered at Lowell, so there's sort of a connection there. Charon, James Christie's wife's name is Charon, and so when Charon was named, it sort of had a personal connection for them. And Nix and Hydra, New Horizons mission. So there's sort of some fun names that we toss around when we look to name these objects. These two satellites are significantly smaller and fainter than Pluto and Charon, of course. So Charon is about half of the size of Pluto. These objects are only a couple hundred kilometers, or maybe 100 kilometers. I think one of them is like 50, one of them is 70 in diameter. So these guys are really small in comparison. Well, the problem didn't stop there. They kept taking data. And I think the end of last year is when this came out, 2 years ago. And so we have yet another satellite. And in this case, they were optimizing on Nix and Hydra, so you can see those even better. The cutout that you see here was a way to blot out the light of Pluto and Charon. And yet one more right here, P5. Now these two don't have names yet, although I think there have been some names proposed. It's really convenient that all of these moons orbit in the same plane. So sort of like the rings of Saturn, all of these moons are in that same plane. However, this has caused a lot of consternation for the spacecraft in the sense that you don't want to fly through a ring of material because the spacecraft is about the size of a baby grand piano, so maybe this podium-ish. And it would easily be destroyed if you, of course, fly it through some ring of dust. And at this point, I believe that this is as good as we can do with the technology we have here on the Earth to actually look for these objects. There was recently a paper that was published, or is in the process of being published, where a modeler has suggested that there could be as many as 10 moons orbiting. But at this point, they're all in the same plane. The trajectory for New Horizons, which you'll see a little bit later, sends the spacecraft sort of in this region, except coming through the disk. So I'm not sure I can point to it here, but the optimal position is to go straight through the middle between Pluto and Charon. You notice that all of this material is outside of the Pluto-Charon area. So if you go through here, you're actually pretty safe. And this would be like three-dimensional, so you won't actually go through that plane. But it's caused some very careful replanning of the spacecraft encounter to make sure that we still have a spacecraft when we get to the system. Now, this is to give you a sense of scale and a sense of surface features. So this is, of course, the US, which we know and love. This is Pluto, and this is Charon, to scale. And it took until we had observed Charon to actually determine that this was actually the size of the system. And I've got a slide later that explains that in a little bit more detail. But these objects are pretty small. This is our best color picture of Pluto and Charon. So we know that they're different colors. And then this is Nix and Hydra. I don't believe the two new ones actually have color information. And I'm not sure which one of these is which. But we know that Pluto has ices at different places on the surface. Pluto is in what's called a vapor pressure equilibrium situation. And so when you sublimate ice from the heated side of the planet, or the object, it then recondenses on the cool side. And so you can move the ices around, redistribute them as Pluto heats in certain places and as it cools on the opposite side. Pluto and Charon are locked in a 6.38 day synchronous period. So if you were on one side of Pluto and you saw Charon, then you'd know you had a moon. If you lived on the other side of Pluto and you looked out, you'd never know you had a moon because they're always seeing each other from one side and not from the other.
Spectroscopically, they're actually very different from each other. So this is the spectrum of Pluto in the near infrared, and this is in again, also in the near infrared. The near infrared wavelengths for these objects are actually the best places to look because we know that they're icy, and the signatures for ices are pretty strong in the near infrared wavelengths. So this is water ice on the surface of Pluto, and so the surface of Charon, which matches up to this. And then this is a methane ice on the surface of Pluto, and a little bit of CO, and this nitrogen line, which actually is related to the nitrogen on the surface as well as a significant amount of nitrogen in the atmosphere. And I'll get to the atmosphere a little bit later. So we know that these two bodies are very different from each other, but it's not unlikely that they formed in some sort of collision, and maybe you redistributed some of the ices between the two objects. So one of the ways that we learn about Pluto and Charon are through occultations. And an occultation is just like your idea of a solar eclipse. So Pluto or Charon is going to pass in front of a star, and you look at the light of either one of them, and as it passes that star, if there is an atmosphere, you end up with a situation like this, where when the light starts to hit, or when the starlight and Pluto start to occult, you have sort of a gradual dip because there's light being refracted through the atmosphere. And then you can measure the diameter of Pluto or of Charon in either case here very accurately. And then when it comes out the other side, and you can learn an awful lot about the atmospheric composition and structure by looking at this particular dip. Likewise, you can do the same thing for Charon. And this was a measurement that we took back in 2006, and you basically see that Charon, it's a very straight dip, which implies that Charon does not have a substantial atmosphere where Pluto does. Now, one of the things about Pluto's atmosphere is that we're expecting, so Pluto's been closer to the sun and is now headed out towards, because of its elliptical orbit, it's come into the 30 AU, and it's headed out towards 40 astronomical units in that heliocentric orbit. And we expect that after a period of time that this atmosphere is going to recondense on the surface. And so one of the important parameters for the New Horizons mission initially, before we had a little bit more understanding of what was going on, was we wanted to launch early enough so that we could get to Pluto before the atmosphere collapsed back on the surface, because we're interested in the surface and the atmosphere, not everything condensed on itself. And that was originally predicted to be, I think, sometime 2015, 2016. It turns out that there's also this thing called thermal inertia, which, if you think of it, it's sort of like when you like heat the asphalt during the day, and then when the sun sets, the asphalt's still warm for a period of time before, after the sun goes down. And so as Pluto's receding from the sun, it has some of this thermal inertia. So it's actually going to keep its atmosphere, we hope, a little bit longer, where we'll be able to observe it before the atmosphere recondenses. So I'm going to play this little video. So this is actually this Charon occultation. So what you're going to see, this is Pluto and Charon and a star. And what you're going to see is you're going to see the star blip out as Charon passes in front of it, which is what happens right here. So this is the light of Charon, Pluto, and the star. This is what happens when when Charon is dipped out, and then you'll see just Charon, and then it'll come back. This is sped up a little bit, but so here we have the pair. There it goes. There's the occultation. It's really cool when you're collecting this data, when that little blip happens and you see it at the telescope, it means that everything worked the way it's supposed to. So now we're in this part of the diagram. And now it comes back up. And so we use this. The other thing that we can do with this type of information is we can determine what the species is that's in the atmosphere. So we know how big Pluto is based on the fact that Pluto and Charon, we can use that to determine the system mass and to learn something about the gravity in the system. And so we can estimate, based on the ices that we know about and based on the gravity, what the planet can actually hold on to. And
So when it was first discovered to have an atmosphere, people thought CO2, maybe nitrogen, and it turns out that nitrogen works really well. It's in terms of being able to Pluto being able to hang on to the atmosphere, as well as it having a lot of nitrogen ice. If we look at sort of extrapolate to the interiors, this is sort of our model for Pluto, where we think it has rocky core, followed by water ice and other sorts of nitrogen ice and methane ice and maybe organics on the surface. And then Charon, which is probably mostly water, but probably some sort of rock ice mixture. The densities of these two objects, this Pluto is like 1.8 and Charon is like 1.6. The density of water ice is 1. And so we know that Pluto is primarily rocky, not just icy, like some of the other objects in the Kuiper Belt. Now, just to give you a historical perspective before we go too far, in the 1700s, we knew about Halley's Comet, and it's a short period comet. So this is a comet that we see regularly, and depending on what your age is, every 76 or something years, it comes around, and it sometimes is a really exciting comet, and sometimes it's kind of bland. But in any event, we knew about Halley's Comet for a long time. There are lots of historical records of comets, sometimes very ominous and sometimes very exciting for the various rulers at the times. The first asteroid was discovered in the 1800s. So this is a picture of the inner solar system. The Sun, Mercury, Venus, Earth, Mars, all the asteroids. And even though this looks really dense, there's also a whole slew of asteroids that are living inside this region. Even though this looks really dense, there's a lot of empty space there. And then we have Jupiter. If we move to the next, so these are all the terrestrial planets. If we move out to the gaseous planets, we have Jupiter, Saturn, Uranus, and Neptune, and again Pluto in this kind of wonky orbit. So the asteroids were discovered in the 1800s, and when they were first discovered, Ceres was called a planet, and after a couple months, there were other objects that were discovered, and they said, oh, maybe this isn't a planet, maybe this is the remnant of a planet that never formed. And so those came to be called asteroids. And Pluto was discovered in 1930. People had thought that there must be some sort of belt of material out here. Number one, because Pluto didn't seem to solve the Neptune orbit problem, but also because if you look at the comet distribution, we see comets that come into the solar system from various different inclinations. So there had to be some source region for that. And as well, that there was no particular reason for the material just for the edge of the solar system just to stop having material. And so they kind of thought there was probably a gradient of something that we should be able to find out here. So this was sort of the work that was done in the 1950s, but there wasn't really a way to observe these things. So Pluto was sort of discovered by accident. It happened to be really bright. It happened to be closest in its orbit, or pretty close in its orbit for us to observe it. And so in 1992, we started to discover these little blue dots, the Kuiper Belt objects. And so if Pluto had been discovered in the 1990s, it would never have been called a planet. And yet it's been a really interesting and really diagnostic object for us for understanding the Kuiper Belt. If you go out a little bit further, one of the other objects that we've discovered is Sedna, which we think is part of the Kuiper Belt, but is sort of on its own special orbit. So we think this is a representation of a larger population of objects. And then if you go out from there, we've got this idea of, so here's Sedna, and then here's the idea of the Oort cloud. And where all of these orbits are mostly in the plane of the solar system, the Oort cloud is thought to be more spherical distribution. So material that was originally between the asteroids, within the asteroid region, or between the giant planets. As the giant planets moved around during the formation of the solar system, that material got kicked out and has resided in the Oort cloud. Every so often we see these objects come in as comets. And then just to give you in a broader picture, we've been discovering a lot of, if you've paid attention to anything in the news, there have been a lot of extrasolar planets that have been discovered over the last 5, 6, 10 years. Actually, 1992, the first Kuiper Belt object was discovered, and the first exosolar planet was discovered. So that was kind of an interesting historical combination. And now we also have a bunch of dust disks around other stars that are basically solar systems that are in formation mode. I like this picture of Beta Pic because in our own solar system we have the asteroid belt, which is sort of the hot disk, and then we have the Kuiper Belt, which is the cold disk. It's further out. So we have this is the Beta Pictoris disk, so you have the asteroid belt effectively, and then a secondary disk, which might be likened to the Kuiper Belt, and they've just blotted out the light of the star so that you can actually see the disk part. We also know that these disks can be controlled by giant planets. So even though there has been, in fact, been some discussion about whether this planet is really a planet, we do see dust disks like this with presumably planets around them that are helping to control the dust ring. We see this a lot in the Cassini data. If you've seen any of the images of the rings of Saturn, it has little shepherding moons that do some amazing things within the rings of Saturn. And if you have any interest in that sort of thing, they're really cool images to watch, very high resolution. And when we study the material properties of this type of dust, we find that it matches up to objects in our own solar system. So this is an object that resides in the Kuiper Belt, and the spectroscopy matches up to what we see around dust disks. So what we're observing in our own solar system, we can then leverage what we've learned from our own solar system, from what's close to us, to better understanding the disks around other stars. So the first Kuiper Belt object was discovered in 1992, and you can see it here. This was discovered by Dave Jewett and Jane Liu. So you see the object moving relative to the background stars. This is just an asteroid that's been moving through the field. Since then, so we started in 1992, found a couple objects, 4 more, 10 more, 2007, and now we have something like 1,600 objects that we observe. We expect that there are something like 70,000, 100,000 objects that are out there. Depends on whether you're talking about big or small relative to how many objects we have there. So we've had surveys now that have been running to try to find these objects. So now Pluto has a context. It's not just an object that's unique out at the edge of our solar system. There's a whole belt of material that we can use to better interpret and understand it. By the same token, Pluto is the brightest one of those objects. And so if we study Pluto in detail, we can learn something. In particular, since Pluto has these small moons that are actually comparable in size to the other objects in the Kuiper Belt, we can use that whole system to help us understand more about the whole system. So how do you look for these objects? I threw this in because this is kind of a fun survey project. So this is the plane of the ecliptic. So if you think about that other plot, this is just the plane that all the planets are on. And each one of these boxes represents a field that we could get to using a 4-meter telescope either in Chile or in Arizona. And each one of these fields has enough stars that we could measure the position of the object very accurately, but it does not have any really bright stars in it because a bright star will saturate a CCD. If you've ever tried to take a picture of the sunset with your digital camera, you know that sometimes gets streaks and doesn't work very well. We take 2 images approximately 2 hours apart of the same field. We match up the stars, so the stars appear white in the images, and we read 1 image into the red color plane in the computer, 1 image into the blue color plane. We match up the stars and we look for moving objects. The length of the streak and the distance between these objects tells us approximately how far away from the Earth or from the sun these objects are. So if you ever looked out at night and seen like a shooting star, you notice that you see the trail and it comes really fast. Near-Earth asteroids are obviously further away than meteorites that meteors that enter our atmosphere, but they're moving very rapidly. So in 2 hours, they move a lot relative to the background stars, and they streak in a 5-minute exposure. The main belt asteroids streak some, they move a little bit less distance-wise, and then these are all little Kuiper Belt objects, the pairs of the images, and these guys are all out sort of in that same region of space that Pluto resides in. This is our current picture of the Kuiper Belt. So I apologize that these 2 slides the colors don't match, but the red objects in this diagram and the blue objects here are what we consider the cold classical disk. We think that these objects basically formed where they are. Maybe they've been moved around a little bit, but not significantly. It takes approximately 300 years for these objects to go around. There's a big gap here because observationally, let's see, maybe the gap's up here.
this has been filled in over time. When we first started the survey, it's really hard to find things in the galactic plane because there's just too many stars, and you'll see a picture of that later as to why. So, we've slowly been filling this in. The white objects correspond to the red objects here. Those are objects that are in mean motion resonances with Neptune. So Neptune goes around the sun 3 times. These objects go around the sun 2 times. They are in orbits in such a way that they will never collide with Neptune, but they are in resonances with Neptune, both here and then other higher order resonances. The purple objects and the gray objects are all the scattered disk objects that we think started out someplace in here in between the orbits of Saturn, Uranus, and Neptune, and as the giant planets migrated outward, they were scooped up and tossed out. And then these yellow objects and the orange objects up here are thought to be objects that started out in the Kuiper Belt and have been interacted with Neptune, and then they get tossed into Uranus and tossed into Saturn. So these are objects that we think are actually fairly dynamically young, but so they're sort of transient, but they're easier at some level to study, in particular the larger ones, because they're physically closer to us. So I mentioned the large Kuiper Belt objects. These are the ones that we might have comparisons with for Pluto. Yeah, question?
I was just going to ask, are all of those objects in the same disk as the rest of the solar system, or in this secondary disk that you talked about?
So this would, going back to you mean the beta pick one, they would all be in the secondary disk. So it turns out the Kuiper Belt is offset from the plane of the sun, or the plane of the solar system, by about 1.5 degrees. It's not a significant factor. It's the invariable plane of the solar system. So there's the plane that we see everything in, and then there's the angular momentum plane, and so it's sort of a difference between those two. So it's a very minor fraction, but yeah, so that would be in the secondary disk. So we have the large Kuiper Belt objects. So we have Pluto and Charon. EL61, which is kind of a unique object, it's kind of egg-shaped, and it's got 2 different moons. It's actually the largest of what we call a collision family in the Kuiper Belt. So we think that we think that Pluto and Charon probably formed through a collision. We also think that EL61 or Haumea formed through a collision. And there's approximately, depending on how you categorize them and what paper you believe, something between 12 and 20 objects that are part of this sort of family. Eris, which is the object that offset Pluto relative to whether it's a planet or not, because it's within the error bars the same size as Pluto. Sedna, which is in a very odd orbit and is probably the closest we can observe at the moment to the Oort cloud, although it's not in the Oort cloud, it's sort of on the inner edge. And then these are some other objects that were particularly large and interesting at the time the plot was created. But we sort of have these large guys, and then we've got a whole bunch of smaller things that are like around 500 to 100 kilometers that we observe. That's all the other points that you saw in the previous plot. Now, this is the only slide that has math on it, and I know some of you saw this earlier today. So why are binaries important? Well, this is what told us that Pluto was not the size of Mars. So when Pluto was discovered to have this moon, Charon, we were able to use Kepler's laws to tell us what the mass of the Pluto-Charon system was. So when you measure the semi-major axis, the separation of the 2 components, and how long it takes the components to go around each other, that gives you the system mass. So at the time in 1978, we realized that Pluto was not the size of Mars. It was less than the size of the moon. You can take this information, and through either a variety of measurements, we actually know this pretty accurately, these measurements, the diameters fairly accurately for Pluto and Charon because of the occultations where you're measuring the diameters explicitly. That's how you get those density measurements out, and how you can then try to construct some ideas for what the internal structure of the object is. So we use this in order to learn something about the physics of the bodies that are in the outer solar system that we don't have. There's been multiple missions to asteroids and such. We've only got one shot at the Kuiper Belt. We've only got one shot at Pluto in our lifetimes. And so we have all these binary orbits that we've been collecting using the Hubble Space Telescope. This is the same object measured at 5 different times where we were looking to get the orbits And we have, like I said, lots and lots of orbits. There are approximately 80 Kuiper Belt objects that have binaries, or that are binaries. We have about half of those that we've measured the orbits for. And so when we do this, that allows us to measure the densities or estimate the densities of these objects. And so we have the density of the terrestrial planets. We know that these are full of iron and silicates and rock. We've got some silicates in the asteroid belt. The giant planets are very low density because most of their composition is the gas. So we've got the cores, but most of these are hydrogen and helium, and then Uranus and Neptune that have lots of methane in their atmospheres. Pluto is out here, and then we have this range of material. We think that the objects that are down in this region, they have a density lower than water ice. So we think that they're kind of like think of a snowball that's sort of not really densely packed. Would be something similar to this. So this is sort of the material that formed outside of the giant planets and stayed there. And then some of these other objects likely got bumped out from between these giant planets and bounced out into the Kuiper Belt. So the model that we use when we talk about the Kuiper Belt and the formation of the outer solar system, this has been talked about as the Nice model because it was basically determined or defined by 4 guys that were working in Nice, France. That's how it got its name. And it's a model that actually does a really good job of explaining what we see observationally. So you have the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, and you start out with all of these objects within like 15 astronomical units of the sun. So Jupiter starts out a little bit outside of where it is right now, so 6 or 7 AU. Saturn, Uranus, Neptune start out much closer in, with a bunch of material in between the giant planets, and then the cold Kuiper Belt that started out maybe around 20 astronomical units, and basically as the giant planets moved, they just kind of got pushed out along with it. And then the idea is that the giant planets migrate. Jupiter migrates in and interacts with the asteroid belt, as well as the terrestrial planets as they're interacting with the asteroid belt. And then Saturn, Uranus, Neptune, you have to conserve angular momentum in the system, and so they, as a result of Jupiter getting pushed in, they get pushed out, they interact with the small bodies, and so we send some of the guys that are in between these giant planets out to make up the scattered disk and the resonant population. The resonant population is kind of a mix of these two because Neptune, as it moves out, can capture objects that are in the right locations depending on how quickly or slowly that happened. Okay. Let me ask if there are any questions there before I continue on to the New Horizons stuff, part of the talk. Okay, so I'm just going to sort of summarize what's going on with New Horizons. They launched in January 19th of 2006, so we're headed for Pluto. And like anything else, the fundamental exploration lesson of planetary science is so that we can get higher resolution images and understand it. This is Pluto at its best resolution with Hubble. This is Triton, which is Neptune's moon, and then this is the Earth's moon at the same resolution. So you know what the moon looks like at high resolution, right? You can take a pair of binoculars tonight, or actually the moon was there when I was driving this morning at 3:30 this morning. So anyway, so this is the resolution of what we would think of the moon if it was at that same resolution. So there's a lot more that we can learn about Pluto by being close to it. So the launch was in January 2006. We will encounter Pluto and Charon July 5th, 2015. And we hope to visit, this is a schematic of the Kuiper Belt, we hope to visit a Kuiper Belt object in 2016 to 2020. And like anything else, for this particular project, persistence has been the key. People started working on this, as I mentioned, back in the end of the 1980s. And so for many people, this was sort of like, like the hallmark of their career to be able to do this. The problem is, of course, it takes 10 years to get out to Pluto. So everybody who's on the mission, who's in a significant position, you have to designate who's going to take control or take over should something happen to you in the meantime. So these are just some different schematics, and it was given a very high priority in the decadal survey. This was the one planet we hadn't visited, the one part of the solar system that we really haven't explored yet, and the other thing that you need is you need the plutonium to get out there at a decent speed and decent rate and to keep going. And by launching in 2006, we were able to use a Jupiter gravity assist. So we knocked 5 years off the mission, I believe, by being able to use that assist. Once we went past that time, Jupiter was no longer aligned in the right place. Would have taken a much longer time. So we would have gotten there in 2020. Maybe Pluto's atmosphere would have collapsed by then, maybe not. This is just pictures of the various people who've worked on this mission here. And then on the launch pad, Alan Stern, and I think that's Alan, and then ready to go. And the project philosophy has really been to do things early, leverage the science, be on time, in budget, and low risk. And so there were a lot of things about this mission that were, I think the spacecraft, if I'm correct, was put together very quickly. Like the time of you've got the money to do it to launch in January was very condensed compared to most other missions. And keep it simple. And we've got some really cool, so you see, pictures of children and stuff. There's been a lot of really kind of fun public outreach related to this project. Now, I don't know a whole lot about launch stages and all that, so I threw this slide up here in case there's anybody who's really interested in how the launch happens. I really can't answer any questions about that, but there's all the components. Our specific goals, so typically when you have a mission, you break down into mission goals of, we have to do this, this is a requirement, these are things that we think are important, but if, an instrument broke, or every time you do, when you build a spacecraft, you want lots of redundancy so that if something goes wrong, you don't lose everything or you don't lose all your science, you can compensate back and forth. So the second part are the important things, and then the group 3 were the desired objectives. So sort of the main things, like the mission is considered a success if this happens, is to characterize the global geology and morphology of Pluto and Charon. At the time when these goals were specified, right, we didn't know about the other moons. Now there's a lot of discussion about, well, can we get pictures of Nix in this place or Hydra in this place, or how do you do all the timing? There's approximately, I think the main data collection is like 24 hours because we're flying through so fast. And so there's lots of, back and forth as to what the most interesting science is that we're going to get out of it and where you want to be and what instruments you want to be using at the right time. We want to map the surface composition of Pluto and Charon and as much as possible any of the other moons that we can get in the right orientations. We want to characterize the neutral atmosphere of Pluto and how fast it's escaping. And then the additional objectives, the time variability of Pluto's surface and atmosphere. We want to get some stereo imaging so you can actually get sort of altitude perspectives. Looking at the terminators so that the split between the dark and light side for Charon and Pluto at high resolution. Looking at composition, different atmospheric species. I won't go into all the details of these, but one of the desired goals was to search for additional satellites and rings. Clearly, part of that has been done even before we get there, and because of the way the mission is designed in terms of the fly-through, I think that we're limited about looking for new ring systems, like when you get really up close. So your field of view is wide, and then it shrinks as you come into the system. But you really want to know what's there before you fly through it. So this is the spacecraft, and you can see it's pretty small, right? There's plenty of people in here for scale. We have a very nice complement of instruments. So you have REX, which is the radio science, which does both science as well as communication. We have this energetic particle detector, the solar wind analyzer, Lori, I'm really mostly an imager, so I'm excited about Lori and Ralph because these are going to get us really nice visible images, and I'll give you some samples of what that resolution should look like in a little bit. We have the star trackers, Ralph, which is the infrared imaging, Alice, which is a UV spectrometer, and then actually this is, again, one of those detectors or instruments that I think is really kind of cool. This is a student dust counter, which was designed by a bunch of undergraduates at the University of Boulder, Colorado. It's basically, to the best of my understanding, kind of like a little microphone, and it's been on since we went through the Jupiter system, and it's been collecting data about how much dust is there as New Horizons is receding from the sun. It's also been really useful, I think, in terms of turning on and off different instruments in the spacecraft, because being like a little microphone, they can make sure that all the doors are shutting and things are happening the way it should. But it's a very well-designed spacecraft. There's a lot of redundancy in the electronics and such. And every time they've turned it on, it pretty much is in like a sort of a sleep mode. And then once a year, I think they turn it on and make sure everything works. When we flew through the Jupiter system for the gravity assist, they turned on all the instruments. In particular, Lori did some nice imaging of Io. And they tested out to make sure everything worked the way that it should. And to the best of my knowledge, everything's working as planned. So as I mentioned, this is a student dust counter, the team leaders, and they had the primary responsibility for the design of it. They have been able to be involved with the project directly. So that's really exciting from an undergraduate perspective, to think that you can work on this NASA mission. That NASA missions are sort of big, large groups of people. So to be able to work with a group of people like this is really neat. This is the current location of New Horizons. So we've made it out past Uranus. This just shows you what the trajectory is. This is just a couple days ago. So we were traveling very, very fast when we left the Earth's orbit. Went and did a slingshot across Jupiter, and then we fly out here to Pluto. And then hopefully onto a Kuiper Belt object that's someplace out here. And so this was the Jupiter science. They had a variety of different priorities for doing that, but the gravity assist was the primary objective going by Jupiter. This increased our speed trajectory to Pluto. And also all the encounter ops practicing, instrument calibrations, making sure that we understand we have all the calibrations before we get to Pluto. And so they studied some of the Jovian meteorology, satellite geology, composition, and such. So it was actually really successful when they flew by Jupiter, and because of all the planning that was done for the Jupiter encounter, they actually went ahead and at the time sequenced all of the Pluto encounter, because they had all the expertise, all the technology. They learned how everything worked before it's a mission that takes 6 or 7 years to get there, and so you can imagine people who are not getting paid to do New Horizons stuff will go off and find other jobs, and then when you want to actually plan everything, you've lost all the expertise for that. So they actually did a lot of the sequencing for the New Horizons flyby during that time frame. And as I said, this is the Jupiter science working as planned. So this is an active volcano that was observed on Io during the flyby. I just think this is beautiful. You can actually see the individual particles, and people are modeling this, and what does this mean in terms of both gravity and the composition and variety of different science goals that you can do with data set like this. This is an image from the Lori imager of Pluto. So from the spacecraft, we can see that. And then, of course, this is another Lori image on the other side of Io and shadow on Jupiter, and Europa and shadow on Jupiter. So this is the encounter geometry. So let's see, we come through here, and with Pluto and Charon, and then the various timing constraints. So you want to do occultation studies for Pluto and Earth and Charon and Earth. This may have gotten rearranged since the time that this slide was put together, because now that they're dealing with the various additional satellites, they're doing some rearranging, I think, of some of the system. But basically, the idea is you want to optimize, everything that you're flying by. I think data starts getting collected about a month out, maybe a couple months out, and then the spacecraft goes through, flies through the system, and continues collecting data. There will be parts of data sets that are sent back right away, so we know everything's working, but it will take a number of months to actually get all the data down back to the Earth once we've collected it all. And then the last part of this is actually what I've been most involved with, and that is finding a Kuiper Belt object to study after we fly through the Pluto system. So
We've been working on this since about 2008. One of the other people I work with, Scott Shepard, had taken some data in 2008 and 2009 using the Subaru telescope, and then a large collaboration of us started up in 2010, 2011, 2012. We have more time this summer. 2012 was kind of a bad season for us. We ended up with a lot of cloudy weather in Chile and Hawaii. But in any event, we have the survey to look for an object to encounter once we get past Pluto. And it turns out that you want to search for an object. The closer you get in time to the encounter with Pluto, optimizes your knowing where you need to look in the sky for an object for the spacecraft to actually reach, because the spacecraft only has so much fuel on it, which means it can only divert so far. Unfortunately, you need to know the orbit of that object pretty accurately before you actually get to Pluto so that you can, retransition your spacecraft. And Pluto happens to be going through the galactic plane, which makes looking for objects a little tricky. This is the resolution. I probably should have switched this one up earlier. This is the resolution of the panchromatic imager. And then this is for Europa, but then this is the highest resolution we'll get for Pluto once we're actually there. So you can already see different ice ridges and crisscrossing terrain and such that you can do all sorts of interesting modeling with. Okay, so this is, as I mentioned, the Kuiper Belt. So this was an image that I took when I was working with Mark Bowie at Sertololo for a different project. But these are two images, and basically you take these two images, you subtract them, and you can get something like this, which is actually pretty impressive given what these two images look like to start with. So this is looking in what we call a dense cloud in the galactic plane area. And so we've collected terabytes of data, looking at a variety of trajectories. So it's the main trajectory, but what you do is you search a wide area, and then the closer we get to Pluto, the smaller that area gets, because, of course, you know more specifically when you're going through the Pluto system and where you're going to end up on the other side. So this is just sort of, the galactic region where Pluto is, and then a variety of different percentages. So if we look in this area, we'll get 50%. If we look in this area, we'll get 85%. We expect to find one or two objects that might be targetable. We've been using these two telescopes primarily for our search. So the Magellan telescopes in Chile, using a wide field imager there, a couple of them, but we've had really good success with the MegaCam imager and just the excellent conditions down in Chile. And then the Subaru telescope in Hawaii. We've had a couple, we've discovered some potential objects, although we do not yet have a specific target. So this is, again, looking for the search grid and how many objects, not how many objects, the star field and the objects that we would be able to potentially find in here is a couple. This is, this little red-green-blue pair is a candidate object. This is the image with the object, and then this is the data subtracted image, and then this is just obviously another way of looking at it. But you can see this is not something that your eye would just naturally pick out and say, there's the object I'm after. We have a list of 26 candidates. We discovered an interesting object, a Neptune Trojan, during our observation. So the first object up there has a paper that's all about it, that tells you all about it from what we've learned. Excuse me. And then we have a couple objects down here, these three that we've attempted to observe with Hubble, one that I'm going to show you an image of, and the other two that I'm still working on the data analysis. So this is, just to give you a sense again of how the data is different from the ground versus in space. This is Subaru, and then this is the HST image in the same field. So you can see the resolution is, and the accuracy is just exquisite with Hubble. And this is one of our objects. We're using Hubble to get a better precision on the position. So you can imagine if you find an object here that you can find the center of the star to some accuracy, but if you go over here and, a similar star, you could get much higher accuracy in that actual position. We're also looking to see if it's binary, because the area where we're flying through has like a 30% binary rate, or binary fraction, and so there's a good chance that the object we find might be binary. And we're also looking to see what sort of information we can get color-wise about it in advance. So I think that wraps up what I have for you. If you have any questions, I'm happy to answer them. If you have specific questions about the New Horizons mission itself, I can tell you that at this website right here, there's a really nice set of science papers. There's one paper that sort of gives an overview of the mission. There's another paper that talks about every instrument and some of the details. So if any of your engineering majors or anything, that paper would maybe be particularly interesting to you. They're all accessible. And there's a variety of other presentations on there that you're welcome to look at. So thank you for your attention.
Questions for our speaker?
How would you determine the age of something? Like you said that some of the stuff might be younger or some of the stuff might be older. But how would you be able to determine that?
Oh, you mean in terms of on the surface?
No, I meant, because I understand that you said that there are certain hot bodies and there are certain cold bodies.
Oh, okay. Sorry, going back to the Kuiper Belt.
Yeah.
So everything in the Kuiper Belt is old, but what we are looking at is how the material is distributed and how it got to where it is now. So the cold classical disk likely formed outside of the giant planet region, outside of Neptune, and we think it's sort of been there since the very beginning. The scattered population, we think, arrived there, so it would have formed all at the same time, but it would have been in place a little bit later because it interacted with the giant planets to get it to that location.
So is it like the galaxy? Is it a similar situation? Because I know we learned that like there's like older stuff rotating at a different angle, and then all the stuff in the disk is younger. Is it the same?
It's a little different in the sense that everything in the solar system formed at about the same time. It's more just dynamically whether it stayed in the same place or whether it moved around. So the timescale the timescale for the formation is something like 10 million years, whereas I think what you're thinking about in terms of galaxy and in terms of stars is that stars are still forming. Most of the stuff in the solar system, the giant planets coalesce fairly quickly, and then so when I talk about young, I'm talking about dynamically young, not physically young. You could think of it, so if you look at just the planets, Io has a very young surface because it's still active, right? It still has volcanoes on its surface. The Earth is very dynamically young because it's got weathering and it's very in that regard. So from a physical perspective, it's those processes that we would think of as being young. But the centaurs, I think, is what you're thinking of, that population that I said was young. It means that it can't live in that area and be stable for the whole age of the solar system. So it had to come in from someplace else. So, yeah. Sorry, I was trying to get the context for the question in terms of the part of the talk. So, okay, great, thanks.
So I guess I don't really get how it is like Jupiter was like sending these things out, or Uranus or whatever. How does that work exactly?
So fundamentally, the angular momentum in the solar system, when you have a disk of material, when you're forming the solar system, you have to conserve angular momentum in terms of, you start out with a disk, it has a particular amount of angular momentum. As the giant planets coalesce more material, they will either gobble things up that are in their regime as they're large enough, or they're going to, if Jupiter moves inward, to compensate for that, in order to conserve angular momentum, you have to move something outward. And so it's basically just an iteration, and depending on, it depends at some level on the size of the objects and the velocities, how they're encountering each other, whether the orbits are crossing, right? If you've got something that's in an eccentric orbit, it's more likely to run into something than if it's in a circular orbit, with something else that's circular. So it's a conservation of angular momentum that's allowing us to determine what that model looks like. That's the physics behind the dynamical modeling. But yeah, good question.
Let's thank our speaker again.